All right, calculus class, we're back, and today we're going to talk about rational functions. So we're skipping ahead. We got some important things in 2.1 of the quadratics, 2.2 is of polynomials, and then we're going to skip to some other things that we use somewhat else in calculus from pre-calculus. So the goal is to try to get us into the calculus stuff fairly soon, because we're still doing some pre-calc type of things. We'll get us into the difference between that. So if you haven't looked ahead, we're in chapter 2. This will be the last new stuff, and then we'll spend a couple days reviewing, and we'll have a quiz for chapter 2. And then we'll move on and we'll get into chapter 3, which is actually kind of the beginning, and it's the basis of all calculus, and it separates pre-calc from calculus. But you can use this stuff some too, so we thought we'd go over this a little bit, give us some more time, make sure we're doing the right stuff. So a rational function. Now a rational function is just where we take a polynomial divided by another polynomial. So if we can say this is the numerator is a polynomial and the denominator is a polynomial, then we call it a rational function. So in our case, I'm just going to go n over d over here, the numerator and the denominator. Over here I have it written out. This will be the more general case. So any rational function is some polynomial with coefficients of a and a degree of n over these coefficients of b with a degree of m. So that's the important part, b and m, that we have that right there, and a and n right there. So here's my domain. Remember, the domain for a fraction, okay, is you're saying, well, what can it be? But there's only 4 things domain can't be. It can't be even roots of negatives, logarithmic functions, inverse trig functions, none of which are applying here, and a fraction, okay? So the denominator cannot be 0. So this domain happens as long as d does not equal 0. There's some d that makes, if there's something that makes the denominator 0, actually I suppose I should put it this way. We should go here. D cannot equal 0. And otherwise it's in the domain. So we take a look at this example function right here, and we say, okay, where's my domain? Well, x plus 3 cannot equal 0. X plus 1 cannot equal 0. X minus 2 cannot equal 0. So the domain cannot be -3, -1, or 2. It's easy as that. Sorry about the glare. We needed some more sunlight in here for you, so hopefully we can read this. So there's my domain. Okay. Now the next part is, remember, the other part is x-intercepts. Okay. So my x-intercepts, and sometimes these are called zeros. So my zeros are when the numerator equals 0. Okay? So we check when the denominator is 0, now we check when the numerator is equal to 0. And I say, when does that numerator equal 0? Well, that happens when x plus 3 equals 0, or x minus 1 equals 0. So that's happening when x equals -3 or 1. And so we think we have these x-intercepts here at 1, 0, and -3, 0. Okay? Otherwise, there are zeros. Now, I'm going to look at that, and I'm going to say, great, that's in general when that happens. However, if there is ever a number that's both in this list that can't be there for the domain, and in this list that makes it a 0, then I got problems, because if I put in that number, I'll get 0 over 0. And that's no good. So, if there's anything on both of those lists, which there happens to be this time, okay? There just so happens that when x equals -3, it's on both lists. So that means that it's not really going to cause a 0. However, I should, a little bit soon, it's still not in the domain. I still can't divide by 0, and I certainly can't take 0 divided by 0. That's called indeterminate. That's even worse than just dividing by 0, because we don't know, is it the same thing, so it's 1? Is it dividing by 0, so it's undefined? Or is it 0 on the top, so it's actually 0? So we call that indeterminate when we have something like that. And in our case of graphing a rational function, those are going to be holes. There will be a hole in the graph when x equals -3. There's a hole in that graph. In other words, it's going to go along, it's going to look good, and then there's going to be a spot where on your calculator you might not be able to see it. But when you zoom in on that, there's going to be a missing piece of that graph, because it's not going to work. As you can see here, if we were just to cancel those, see how we have those 2 factors, x plus 3 on the top and x plus 3 on the bottom. If we cancel it, this will be the graph. Okay? So x minus 1 over x plus 1 times x minus 2 will actually be the graph that I'm going to be looking for. And it's about time that I give this maybe a name. We'll call this f of x in this case. So there's a hole when x equals negative 3. So what I'm going to do is I'm going to figure out what would this have been at negative 3 by reducing this first and saying, negative 3 minus 1 over negative 3 plus 1 and negative 3 minus 2. Because this function that has the reduced part gone is going to act the same as the full function that we have for f of x, except for it's going to be missing the hole. It's going to be continuous there. And so that's what we're going to do, is we're going to pretend like, all right, this is already canceled, and we'll plug that in and see what we get. Negative 3 minus 1, negative 4, negative 3 plus 1, negative 2, negative 3 minus 2, negative 5. And what does that leave me with? That leaves me with, 4 over 2 is the 2 on the top. And we're going to have negative 4 over negative 10, so over positive 10, so negative 2/5. Okay, so there's a hole at the point, now we know, negative 3, negative 2/5. There's the spot where there's a hole in the graph. So we've already taken our function, figured out its domain, figured out the x-intercepts or zeros. Okay, you can say x equals if you want to get the zeros. Figured out the x-intercepts. And then because there was something in common, that was where there was a hole. All right? Now, if there is nothing in common in these lists, then we start going and we start talking about the next thing, which is a vertical asymptote. Now, you guys might remember these from Algebra 2. Okay? Vertical asymptote here will happen when the denominator equals 0. So these are the times that were the domains, when the denominator equals 0. But a vertical asymptote is a line, so I have to write this as an x equals. So when the denominator equals 0, we already figured out when this was, all of these. So we're going to call this when x equals negative 1 and when x equals 2. Now there's a very important thing here. You must write those as equations of lines. You must have the x equals in there and a new x equals, because x equals negative 1 is a line. It's a vertical line with an x value of negative 1. Okay? X equals 2 is another line. Now notice, I did not put a vertical asymptote when x equaled negative 3. Why not? Because there's a hole there. There can't be a hole and a vertical asymptote at the same place. There's going to be one or the other. Because there's a hole at that location, we know that, not a vertical asymptote. It's one or the other, but they're still not going to work. And so now I'm starting to get a picture of what the graph of this rational function might look like. I have its x-intercepts. I know things that don't work. I know when they're vertical asymptotes, and I know when they're holes. Then all I would need to do after that is there a horizontal asymptote? Is there something as I go off to infinity, like the polynomials, so I went to negative infinity, does this take off forever? Or does it level off somewhere? Okay? And as I go to positive infinity, does it take off, either up or down, or does it level off? And that's called a horizontal asymptote. What does it approach as it gets to infinity? Now, unlike a vertical asymptote, which can never be crossed, because you can't have, when x is 2, if it's undefined, you can't tell me that it's going to go there. Horizontal asymptotes, we can wiggle and we can go across there, and then all it has to happen is eventually, as I get to infinity, it has to approach. So, common misconception in my classes have been that they think that this doesn't have a horizontal asymptote. When in reality, as long as it keeps getting closer and closer to that value of 0, there's a horizontal asymptote, even though it crossed many times back here. Okay? And that horizontal asymptote would be at this height of 0. We might have a different function that might level off and go like this. Okay? And if that height that it levels off at is, say, 5, there's a horizontal asymptote at 5. And so these functions will have those things as well. They'll have horizontal asymptotes where it levels off. Now, the horizontal asymptotes get us into a whole other category. So, let's make sure, I hope we can see this. We're going to have to put some cases over here. So much for this. And I might move this over just to make sure that we can see these, because this is really important. There will be case 1. All right? And case 1 is where the denominator has a higher degree than the numerator, excuse me. So when m is greater than n. Okay? So when m is greater than n, we're going to have the denominator has more power. What happens in a fraction when the denominator is really big and the numerator is small? When the numerator is like 2 and the denominator gets really big, 1,000, 1,000,000. And as you get larger, the numerator might grow up to like 5. But the denominator is 7 billion. That's going to get really close to 0. So if the denominator has the power, case 1, if the power degree here, m, is more than the degree up there, then I have a horizontal asymptote. We'll call it HA for horizontal asymptote. We have that right at 0 when y equals 0. Okay? There's case 2, and that's when they're both the same. Now the numerator and denominator have the same power. Okay? And if they have the same power, that means that there's just as much power up here as up down there, and so that's all going to reduce to what's this coefficient and what's that coefficient. There's a horizontal asymptote when y equals the leading coefficients. You just divide the leading coefficients and that's where that's going to be. Now, case 3 is obviously when m is less than n. So the numerator has more power than the denominator, and that'll be on the next video. Okay? Let's stay with these first two for right now. Okay. So in our case over here, what do we have for our f of x? Well, this bottom has 1, 2, 3 factors. The top has 2. The bottom has a degree 3. The top has a degree 2. The denominator has more power. So for our case, we are talking about a case 1 here. And y equals 0 is a horizontal asymptote. So if I go to graph this, putting together the things that I kind of know right now. Negative 3, 0, 1, 2, 3 is a 0. Okay? 1, 0 is another one. Vertical asymptotes at x equals negative 1 and x equals 2. Alright? Do we know anything else about this? Well, let's see. I know that as I go off to infinity, it'll be at 0, and I go to negative infinity, it'll be at 0. And we're at there. So, that's really interesting. Want to know it better? Put in a couple points. Check it out at negative, what is that? Negative 2. At negative 2, what do we get? You know, at 0, what do we get? At 0, we get negative 1 over 1 times negative 2, which would be negative 2. Negative 1 over negative 2 is 2, so we go up 2. So we're going to have this. All right? And then I think, let's see, as I approach here, it's going to go to negative infinity. And then let's see, as I get to the left of negative 1, so let's try in here negative 1.1. That's going to be negative 2.1. Negative 1.1 plus 1 is negative 0.1. And that's going to be a negative 3.1. And so that's going to be a negative over a positive. Alright, and so as I get to there, a negative divided by positive is a negative, it's going to be down here. And we're going to have something that goes like that. Okay, get past, just past 2. Just past 2. So if I got a vertical asymptote there, just past 2, 2 minus 1 gives me 1. Alright, 1.1. And then just past 2, if I add 1 to it, that's 3.1 times 0.1. Those are all positives. Okay, a positive over a positive is going to be a positive way up here. And so we're going to have something that's going to do something like that. And so without even using a calculator, I have a pretty decent idea of what that graph looks like. Now, you can go to your calculator and you want to confirm all this, and we'll do that on many of them when we get done to see if we've done that all right. All correctly, excuse me. See if I have time here. No, I do not have time. Okay, so that's going through that first one. Stay tuned for the next video, and we'll go through a case 2 example, and then what to do if we get to case 3.